Hi everyone, I'm Sajidh. So I'm from INCOIS, Hyderabad. So INCOIS is a organization under the Ministry of Earth Sciences. So we provide ocean-related service to the whole country and the Indo-Pacific region. So our main services are basically we do sea state forecast, wave forecasting, tsunami warning, and we also do climate-related services. So this work was actually done as a preliminary study for the selection of coupled models for dynamic downscaling for the Indian Ocean for future projections. So this for this work, I am just presenting just a part of what we have done. So we have looked at how the dynamic sea level is represented in the CMIP6 models, particularly for the Indian Ocean. So just I'll give a brief introduction on why this work is important. So this figure basically shows what the population, the coastal population residing in each coast. So the red areas denote a very high population density, and you can see this area in particular in the Indian Ocean rim countries and the Indo-Pacific rim houses a large chunk of the global population, and a rise in sea level. Any amount of rise in sea level is going to cause a lot of infrastructural and damage to human life. So our objective is to provide services that will help in inform policy making. So this work is done as a precursor to that, and this basically looks at how coupled models simulate the sea level. So we all hear about this IPCC reports about 2-degree warmings in the future. The sea level will rise by this much in the future. So they basically use these coupled models to rely for these predictions. So we are checking the fidelity of these models. So usually when we are talking about global sea level rise, we are talking in a global sense, the global mean sea level change. But it's not the case for regional studies. So regionally, this sea level change can have a very distinctive spatial fingerprint, and we'll be looking at how this regional sea level is going to affect the Indian Ocean. So this IPCC, that Intergovernmental Panel on Climate Change, basically relies on climate models for this predictions, and we'll be looking at their fidelity. So I'll just give a brief information about sea level and how it's measured. So basically, the sea level is the height above the geoid, and we all know what the geoid is. Geoid is just an equipotential surface of the Earth's gravity field, or it's the shape the world's ocean will take if there are no other disturbance, like there are no winds or waves acting upon it, what the shape of the oceans would be. So we define the dynamic sea level as the height between the geoid and the elevated sea level. It could be positive or negative. So we'll be using dynamic sea level for our studies. One thing to note is dynamic sea level does not include the effects of glacier melting and water inputs. So when we are dealing with altimeter products, it usually have these components included in that. So it will have a component of wind-driven sea level change associated with density variations due to thermal expansion, salinity changes. So we'll just remove the changes that are happening due to freshwater or glacier input water. So we'll just, in each time step, we are going to remove the global mean to ensure that we are just dealing with the dynamic sea level. And we'll be using 20 years worth of data from the AVISO, that is a satellite altimetric product. So we'll be using purely observational data to validate our models. So when we are talking about these models, we are actually talking about the CMIP project. So the CMIP project, at least some of you might have known about this. So this is called the Coupled Model Intercomparison Project. So it's a project that brings together various modeling groups from all over the world to provide us with standardized model outputs of various parameters. So there's all over the world, different modeling centers are contributing to this project. So this is the newest phase, which is the 6th phase. So previous there was a CMIP5 and CMIP3 as well. So we'll be using around 27 models from this project to study the sea level in a multi-model mean context. So a brief introduction about the CMIP6. So it has a set of predefined experiments, some specialized experiments and so on to study different climatic phenomena. So to study internal modes of variability associated with Earth system, you can use pre-industrial control runs. For CO2 responses, to study the CO2 response, you have different CO2 experiments. And to study the present climate, you have the historical runs that extend from 1850 to 2014. And for projected changes, you have studies under different scenarios, so under different emission scenarios. So we'll be using, mostly using the historical runs, and for some part of the study, we'll also use the scenario map as well. So these are the major variables we are using. So dynamic sea level, global thermospheric sea level, and surface wind stress. Why we are using global thermospheric sea level changes, I have told you before, the global mean at each time step is considered 0 for the dynamic sea level. So basically, our models are volume conserving. So we cannot have an addition of water in each time step, but we have to account for the global mean change as well. So the models will compute the global thermospheric sea level change as a separate variable, and will add that to the dynamic sea level to get a better estimate of the sea level change. And surface wind stress, because sea level is driven mostly by surface wind stress through upwelling and downwelling dynamics. And we'll be using two experiments, historical simulations from 1850 to 2014, and projections under two emission scenarios, SSP 4.5 and SSP 8.5. So these SSP, basically, they are just some scenarios that what could happen in the future. So this SSP 4.5 is a mid-emission scenario, whereas this SSP 8.5 is a high emission scenario. So this 4.5 and 8.5 denotes the radiative forcing that is going to be the case after 100 years, or by the end of 2100. So we'll be just looking at both of these scenarios to see how the sea level will change by the end of this century. So as I mentioned before, the sea level estimates are devoid of water from ice and glacier melts, and the global mean at each time step is removed for consistency, both from the models and the observations. So let's look at the mean state of the sea level. So this is the mean state of dynamic sea level calculated from the observation, that is the satellite data from 1994 to 2014. We limit it to 2014 because the models are only run up to 2014. After that, the scenario map takes care of the run. So the historical runs end at 2014, and the observation only starts from 1993. So we just take a 20-year window to study the mean state. So this is the observation, and this is the model mean. So the model mean is, as I have said before, it's a mean of 27 models, and both of these kind of look similar. If you look at the pattern correlation, most models have around more than 0.9 in pattern correlation, but this is the bias. So even though the pattern is similar, there are some consistent bias in the sea level estimates. So especially there is a gradient in the sea level bias, which is higher in the western side and lower in the eastern side. It's mainly because there are some misrepresentation in winds and currents. That's some research are still going on regarding the biases in the mean state. And these biases are important because it can affect how the projections are going to be. So if you do not have a good representation of mean state, our confidence in the projections are going to go down. So we need to have a good representation of the mean state. So this is the zonal averaged DSL, zonal wind stress and wind stress curve, and we can see there is a positive bias for all models. This dark blue line is the multi-model mean, and the dashed black line is the observation, and the individual lines and the shading shows the spread of the models. So all over we can see there is a positive bias which is a bit high in this region. And some notable difference in the wind stress is a larger difference in the southern ocean region. So this is possibly due to the displacement of the equatorial and the mid-latitude westerlies. So this representation of wind stress has to be better in order to get a better representation of the mean state. And this is just the bias of the zonally averaged DSL. So this is from the equator to the 30° north, basically the North Indian Ocean. This is the Southern Indian Ocean, and this is the Southern Ocean, that is from 30 south to 60 degrees south. So the bias is, this is the RMSE, and we can see for each models, these are the RMSEs, and it is quite large for the Southern Ocean. Now we come to variability. So when dealing with variability, we are looking at the standard deviation of DSL in time. So we are using a 20-year data, as we said before, as I said before. So this is the total variability, which is an unfiltered data. So this is the annual climatological variability, and this is the interannual. So interannual is basically total minus annual. So the main thing is the multimodal mean fails to capture the variability in a lot of places. This is mostly evident in the ACC region, the Antarctic Circumpolar region, and near the Agulhas current, because this is a very eddy-rich region, and our ensemble only has around 4 high-resolution models. So it cannot really pick up the dynamics of the eddies, and hence this bias in the variability is very pronounced in the Agulhas region. And in the bias is lowest in the annual CSURF annual variability, but when we look at the interannual variability, it's the same case as the total variability. So the problem with using a 20-year long observation is that there could be signals that can cause, because we are just choosing the time period from 1994 to 2014, there could be signals that are not matching with observation, because these CMIP6 models are free-run models without any realistic initial condition. So we can expect the magnitude and spatial features of variability to be the same, but we cannot expect the timing to be right. So to ensure that the choice of our time period does not bias our results, we run a moving window analysis throughout the entire period from 1850 to 2014. And this is basically the spread of the pattern correlation between the observed variability and the model variability. We can see that even though there is a spread, there is no considerable spread in each model. So we say that it's okay to use the 1994 to 2014 data for the variability analysis. And another main feature we look at in the Indian Ocean is the equatorial sea level slope, because Indian Ocean is mainly influenced by climatic modes such as El Nino, IOD, and so on. So the equatorial sea level slope is needs to be properly represented for a good representation of these climatic modes. And if this is basically the sea level averaged over 2 degrees north, 2 degrees south, and we can see that for the multimodal mean, this sea level slope is almost non-existent for most of the parts. So this basically biases the variability, or biases the models towards an IOD state. So these are the EOF, first modes and second mode of EOF for the interannual DSL. So we can see that spatial patterns of variabilities are caught very well. But the thing is, the first mode almost captured 30%, the first mode almost explained 30% of the total variability. It's only 16 for the observation. And it explained 10% for the second mode, where it is only 6% in the observation. So this representation of equatorial winds is the reason for the misrepresentation of equatorial wind stress is the main reason for the misrepresentation of sea level in the equator. And this biases the models toward an IOD phase, and this kind of enhances the variability issue, enhances the issue with resolving variability. So as I said before, our actual objective was to select a bunch of models based on their performances and use them to downscale it for a higher resolution model, a regional high resolution model. So this is just a precursor to that analysis. We were just looking at how the skill in resolving the wind stress curve is against resolving the sea level. So we use this Taylor skill score metric to just weed out some worst performing models and select some 10 or 15 best performing models. And then again, we'll do some objective and subjective analysis to select the best performing 10 models. So this work is published, and we have selected 10 best models that are good for the Indian Ocean region. So we have also looked at the projections. So this is the projection for the sea level by 2100. So this change is actually the difference between the DSL averaged over 2080 to 2100 and 1994 to 2014. So this is the projection under SSP 2 4.5, and this is the projection under SSP 8.5. This is the similar thing for the wind stress vectors. So the different scenarios only makes a change in the magnitude. Otherwise, the pattern looks almost similar. So there is a higher, there's going to be a higher sea level rise in the Western Basin in the Arabian Sea, and there's going to be a higher bias in the same pattern can be seen in the SSP 5 8.5, but with a higher magnitude, obviously. But the South Indian Ocean shows actually a sea level drop, but this is showing all positive because I have added the global thermostatic change, which is positive for all models. So this is basically our study. So we have selected these 10 models based on different subjective and objective criteria, and we'll be using these for regional downscaling using a high resolution model, so that we can have some projections for the Indian Ocean, so that could contribute to policy making. So thank you for listening. That's it.
Time for a few questions. Sajidh? Students? Any students? Anybody else? Okay. Well, I have a question for you. So you said you disregarded, or you didn't take into account glacial melt, or
I know.
do you think the models would the model responses would be significantly altered?
Yeah, because these models does not have an interactive ice component, basically. Right. Some models have, most models doesn't have. Okay. So if we include that, it would be drastically different, because that almost account to the same amount of change as the thermal expansion.
Yeah.
So we need that actually, but
yeah, so it's not available.
It's not available. That's the reason. Hopefully, it will be available in the future.
Yeah. Any other questions? Thank you, Sajidh.
Thank you.